Interpolation search. Interpolation search is an efficient algorithm for sorted arrays, especially when the elements are uniformly distributed. So, whenever you see that your given array is uniformly distributed, the values in the array are uniformly distributed, you can go for interpolation search. Why is it called interpolation search? Because it interpolates the probable position of the target based on its value and the relative range of array. So we'll see how this is done. So how it works is it uses the value of the elements to estimate likely position of the target. And how does it do? It does something similar to how we search for a word in dictionary. How do you search for a word in dictionary? Let us say in dictionary you have range from A to Z. This is your range. So this much is your search space. And you want to see for some word. Let us say you want to see for tiger. Tiger is the word you want to find from this dictionary. What would you do? Would you simply open the middle part of dictionary and start searching? No, you would first think, what is the probable position of the word tiger? And from your logic, you know that T comes somewhere towards the end in this list from A to Z, which means instead of opening dictionary in the middle, it's better that if you open some page over here, there is a chance that maybe in the page that you opened, you would directly find the word tiger. It's a probability. So in order to increase your chances of finding the word tiger in the page which you are directly opening, what would you do? You would generally directly open a page which is towards the end of the dictionary. And maybe you open this page and you found that in this page words are starting with S. Okay. So from this, what do you understand? You understood that it already reached S and the next letter is T. So the word tiger would be found somewhere near here. This is what your logic tells you. So the next time when you want to pick another page from here, what would you do? You know already this much part is eliminated out. There is no probability of finding the. But here, would you again take the half point in the remaining space? No. What would you do? You would take somewhere over here, very close to S, because you are aware that T comes just after S. And because of that, your chances of directly opening the page which has the word tiger is higher if you open a page which is closer to S. So you would use this logic and next time open a page which is towards S but towards from the right of S. So this is what you will do. Similar to this logic, in interpolation search, whenever you are going to select next position to search for, you will find the position by using some logic using which you will estimate. So let us find the formula to estimate. If it is this particular situation where you want to see the word tiger, how would you estimate page number? If you want to mathematically estimate, what is the very basic idea that is coming to your mind, or the first instance idea, the naive idea that's coming to your mind? I'll give you that the page starts from 0 and goes till 1000. In this case, one possibility can be this. You know there are 26 alphabets. A is the first alphabet and Z is the 26th alphabet in English. So, and you know there are 1000 pages from 0 to 1000. So 1001 pages. So how will you estimate? One option to estimate is this, that you know you are searching for tiger. You will see what fraction of this total dictionary should be the point at which you open it. So how will you determine the fraction at which you can find T? In order to find the fraction, your denominator will be the value of Z minus A. And in the numerator, it will be T minus A. So here I'll substitute with numbers. Z will be 26, A will be 1. Okay, I'll substitute the alphabet number. So Z is 26, A is 1. Similarly, T is 20th alphabet. So 20 minus 1. So this is what is the fraction. So my fraction is 19 by 25. So I know in this complete dictionary, if I open somewhere near 19 by 25 of the dictionary, then I have higher chances of opening a page which is starting with T. That is what I know from my logic. So this is the fraction. And what is the page number, exact page number? How will I identify the page number? I'll do 1000, which is the maximum page number, minus 0, which is the minimum page number. If I do this calculation, I'll get one particular page number, which according to my present logic is the most probable page in which I can find tiger. But I'm making an assumption that all the alphabets are uniformly distributed. That is, somewhat the number of words starting with A will be same as the number of words starting with B, which will be same as the number of words starting with C, and so on. This is the assumption I am making. I'm making the assumption that it is uniform data. So that is what I said initially, that we make the assumption that data is uniform. So even in dictionary, it's not actually uniform, but if you use this logic, you can somewhere near reach near the page you are searching for. The same logic we'll convert into numbers and use for arrays. That is what is called interpolation search. Let us see how to form this equation. In case of interpolation search, you will have an array, and your array, the input array, will have first index, we'll call it low, and the last index, we'll call it as high. This is the array you are having. And in this array, you want to find some target value. Some target value is what you want to find. So how will your formula look like? Formula will look like, so here low is not 0, so I'll write something like low plus, what should be the fraction? The same logic which we used in that dictionary. So your maximum value is high, minimum is low, and you are checking for something which is a target value. So that target value minus array of low. So here we are making the assumption that the array will be sorted. So this will be the smallest number, this will be the largest number. AR of low divided by array of high minus array of low. So this will give you the fraction. So target minus array of low, which means your target value may be some 50 or something. Array of low may be first value in the array may be 10, last value in the array may be 65. Maybe this is your array. So in that case, my fraction is target minus array of low divided by array of high minus array of low. That is last element minus first element. Array of high minus array of low means last element minus first element. And the numerator is target minus first element. This is the fraction. I have to multiply this with the range of indices so that I get the index at which I want to go to. So the range of indices is high minus low. So this is my formula. Using this formula, I will estimate one particular index in this array, which according to me is the index in which I can find the value I am searching for. So here I am making a guess, but this is an intelligent guess. This is the speciality of interpolation search. You are interpolating the probable position of the target. So then what you do is, you are going to use the same logic as that of binary search. In binary search, what do? You generally go to the middle of the array, check with that element, and if the target value is equal to that element, then you will end the search there. If the target value is larger than element, you will move towards the right. If target value is lesser than the middle element, you will move towards the left part of the array. This is what you do in binary search. But the problem there is, you're always going to look at the middle element in your search space. But you know, if the data is uniformly distributed, using that logic in interpolation search, that is using this particular formula, you have an option to estimate the position, and in that case, you can directly go to one position which is probably the position of your search value. Which means when you go to that position, there is a probability that you can end the search right there if you find the target value. So this is the logic used. Otherwise, the rest of the logic is same as binary search. If it is not the value, then you will go to the right or left side of the target value, depending on whether the target value is larger or target value is smaller. Right or left of the position where you reach, depending on whether target value is larger than the value in that position, or target value is lesser than the value in that position. So you understood the logic, right? So this is the position estimate. Here I'm estimating position using this equation, and let us say I found some position and I'm searching for 50, and the position that I found is some index 5, and in index 5 I am having the value 44. So what will I do? I'll check my target value, I'll compare with 44. It is not 44, which means I have to go to the right side of array. I can eliminate left side of the array and I only have to consider right side of the array. This is what is the logic in interpolation search. So the logic is same as binary search. The only difference is in instead of middle element, I'll be finding position using this formula. So let us write pseudocode and understand this. Then we'll see for the space and time complexities of this algorithm. So pseudocode. Let us see the pseudocode. So in order to write the pseudocode, you want to only know the logical parts. That is, what is the equation to find the position? That is number one. Second thing is, once you find the position, what should you do? You should check whether the value at that position, AR of position, is that equal to the target. If it is equal to target, you can stop the search there because you already found the value you are searching for. If you are not able to find it there, then you have to check whether array of position, is it less than target value or is it greater than target value, and depending on whether it is lesser or greater, you have to go to the right or left side of the array. So let us write the complete pseudocode for this. Interpolation search. Let us say interpolation search of array and target. So from this array, you are going to find out this target value. So what are the variables you want here? You want the low and high indices of the array. So low, we'll say low is 0, assuming that the array is 0 indexed array. And what is a high value? High will be, we want the maximum index of that array. So we'll say it is length of array minus 1. So this is the last index in the array. So we got low and high values of the array, that is for the range of array, not the exact value. These are the indices, low and high indices of the array. Now we can start a while loop. In that while loop, we have to run till we find the value. So what should be the conditions for the while loop? One thing is that the value of low should always be lesser or equal than the high. If it is larger than high, that means you are not able to find the value in the array. Maybe the value is not present. What are the other conditions? Your target, whatever is the target you are searching for, that target should be greater than or equal to array of low, because low is your minimum value. So your target has to be greater than or equal to this. Also, your target should be lesser than or equal to array of high. Both these conditions should also satisfy. So these are the three conditions, because if these two are satisfied, then only you can find the target between low and high. That is why we are doing this. Keep in mind, it is a sorted array. So we'll start with the while loop. While, what are the conditions that we want? First is low should be less than or equal to high. This is the first condition. What is the second condition? Second condition is the target should be greater than or equal to array of low. So this is the second condition. Array of low. This is the second condition. And what is the third condition? Your target should be lesser than or equal to array of high. So these are the three conditions that you want in your while loop. First one is your lower index should be less than or equal to higher index. Your target should be greater than or equal to the lowest value in your search space. Target should also be lesser than or equal to the largest value in your search space. These are the three conditions. Inside the while loop, what should you have? First, how do you estimate the position? In case of binary search, you simply estimated mid value. In case of interpolation search, you have to estimate the position. So how do you estimate? You estimate as position is equal to low plus, so this is the formula that we found in the beginning of this lecture, low plus target value minus array of low divided by array of high minus array of low. So this is the fraction, and once you get the fraction, what is the next thing? You want to multiply it with the range of indices into high minus low. So you multiplied with range of indices. This is the position that you have estimated. Once you estimate the position, what is the next step? You need to, now you got the position. Now you need to see whether this position, whatever is the value in this position, is it equal to the target value. So if AR of position is equal to target value, if it is the target value, that means your estimation was correct. You correctly estimated the position, and you can directly return position. If you already found the target, then you can return the position. If you didn't find the target, if this is not the case, then else what should you do? You should check whether array of position is lesser than target. If array of position is lesser than target, then what is the case? If it is lesser than target, that means the target value is larger than the value at this position, which means you only need to look at the right side of this position. Whatever is your search space will now decrease to the part which is to the right of this position. To this right of this position means you have to modify the value of low. That is what you want to do. So how will you modify value of low? Your value of low will be modified to position plus 1, because you already know whatever is there in position is lesser than the target value. So the target value is either in the position next to whatever is the present position or to the right of it. So that is why you are changing low value to position plus 1. Else if what is the other case? So ideally I only need to write else here. I'm writing else if so that you clearly see what is the condition here. Okay. Otherwise this is the last case. So you simply have to write else AR of position is greater than target. If AR of position is greater than target, what should you do? You should change the value of high, because in this case the target value is larger than the value at the position, which means you want to see the array towards the left side of the position. So you should not alter low value. Instead, you should alter high value to the left side of the position. So you should alter high is equal to position minus 1. This is what you want to do. So when you run this while loop, by the end of this while loop, wherever this while loop will get to end is when you find the target value. That is, whenever you find that in this position whatever is there is actually your target value, that is when it will return. So if this continuously runs, comes out of the while loop, still it is not returned, that means one of these conditions were violated. That is, you were not able to find the value in the array. So if you are not able to find the value in the array, then you should return something which shows that the search was unsuccessful. So I'll return, what will you return? You will return minus 1. This is if the while loop is completed and you are still not able to find the value, then you will return the value minus 1, indicating search is unsuccessful. That is, in the given array, the value, the target value is not present. That is what you're saying. So what is the time complexity of this? So we always see for worst case time complexity whenever you want to talk about time complexity. That is what we already do, or always do. But here the worst case time complexity is order of n. It is not order of log n, because even though it works like binary search, the problem is we are estimating the position. We are not always taking the middle position. In binary search, we were able to say it is log n because every time we were taking the middle position, which means at every step you are decreasing the array size to half. So every time you were doing by 2 to the array size in binary search. That is why in binary search you are able to come to a time complexity of order of log n. But in case of this technique of interpolation search, you are not always dividing array into two equal halves. Instead, maybe you will divide this array of size 1000 into one piece of only one element and the second piece of 999 elements. So any of such divisions can happen, and because of that you are never guaranteed an order of log n time complexity. Time complexity is order of n in worst case. But there is a catch. The catch is this particular algorithm can provide you an average case time complexity of order of log n in case you have uniform data, and this is why you need this algorithm. The whole purpose of this interpolation search algorithm is that the average case time complexity of interpolation search beats binary search, because in binary search we know it is order of log n. But in case of interpolation search, the average case time complexity is order of log n when you have uniform data, and this beats the performance of binary search. And this is where for searching interpolation search comes handy.